Today I will prove the proposition which characterizes metric connections. Precisely, we have to prove that 7 statements are equivalent. I will not copy them on the blackboard for saving time. I will recall each of them when I need. So I have characterization of metric connections. I will prove that statement number 1 is equivalent to statement number 2. Then I will prove that 2 is equivalent to 3. Then that 1 is equivalent to 4. Then 4 implies 5, which implies 6, which implies 7, which implies 4 again. So let's start by the proof that 1 is equivalent to 2. Statement number 1 says that nabla is compatible with G. That is nabla X of this inner product is equal to nabla X Y inner product Z plus Y inner product nabla Z along X. Instead, the statement number 2 is the following: G is parallel. That is the total covariant derivative of G. This is identically 0. The proof of this equivalence is easy if we use the fact that the total covariant derivative of G is defined by this formula. Now let's observe that this is a function and this is a vector field. So this is something which can be written as x acting on a function f, and we know that this is equal to this. So the first term is exactly this one, this term here is nothing but then the inner product of these two vector fields, and this term here is nothing but then the inner product of y and this covariant derivative here. So it is clear that we have this identity if and only if this is 0, which means total covariant derivative identically equal to 0, that is G is parallel. Now I have to prove that 2 is equivalent to 3. Three means that if EI, E1, E2, En is a smooth local frame, then the connection coefficients of nabla satisfy this formula gamma ki LGLJ plus gamma kj LGIL. This is EK acting on Gij. In order to prove this formula, it's enough to look at the components of this total covariant derivative in terms of this smooth local frame. Precisely, we use a proposition 4.18. The symbol I will use for the components of this total covariant derivative is this Gij semicolon K. This is Pk Gij minus gamma KIL GLJ minus gamma KJ LGIL. So it is clear that if G is parallel, that this is identically 0, then this must be 0 for each K. Now I have to prove that 3 is equivalent to 4. The statement 3 is still on the blackboard. So what is statement number 4? If VW are smooth vector fields along a smooth curve gamma, then we have this formula ddt of VW. This is dTV W plus V dTW. How to prove this equivalence? Simple. Suppose that gamma is defined on an interval I, fix T0 in I, and let x1, x2, xn local coordinates in a neighborhood of gamma T0. Unfortunately, I have to erase. Sorry, I made a mistake. I don't want to prove 3 equivalent to 4, but 1 equivalent to 4. Excuse me. So, if I have these coordinates, I can write down V and W in terms of the basis the delta 1, delta 2, delta n. So I have V equal Vi delta I, W equal Wj delta J, where Vi, Wj are smooth functions. So I have to use now condition number 1, statement number 1, which is this. With the vectors delta I, delta J, which are extendable. So let's make the computation. If I replace these here and this here, I will get ddt of this inner product equal to ddt of Vi Wj delta I delta J and this is equal to the sum of several terms. The first one is v dot I wj delta I delta j plus vi w dot j delta I delta j plus vi wj dt. Sorry, I should write nabla gamma prime t delta I delta j plus vi wj di nabla gamma prime t delta j where here I'm using the fact that dTv equal nabla gamma prime t v at, where v is a vector field along a curve which is extendable and its extension is v tilde. In this formula I have v equal di or dj, sorry, delta I or delta j, and I am using the same symbol for their extension. So this is why now we have that from this term from these terms we get only dT v comma w plus v dt w. This term is the sum of this term here and this term here, and this term here is the sum of this one and this one. And now I have to prove that 4 implies 5. This is the statement which says that if VW are parallel, along a smooth curve, then this inner product is constant along gamma. If V and W are constant, then sorry, if V and W are parallel, then this is 0, and this is 0. If you replace these identities into this formula, you get that this derivative here is 0, which means that this inner product is constant. Now I have to prove that 5 implies 6. The statement 6 is the following: given a smooth curve gamma in M, every parallel transport map along gamma is a linear isometry. So if phi holds true, then I have to prove that if V0 W0 in T gamma T0 M are two arbitrarily chosen vectors, then the inner product of this parallel transport coincide with this inner product. Since we want to use 5, we have to construct two vector fields which are the parent transport of these two vectors. Precisely, let BW the parallel transport of V0 W0 that is VT0 is V0, WT0 is W0, and VT1 is T0 T1 gamma V0, WT1 is P gamma T0 T1 W0. Since 5 is true and V and W are parallel, then you have that Vt1 comma Wt1 is equal to Vt0 comma Wt0, but this one is exactly this, and this one is exactly this. So we proved that statement number 6 is true, holds true if 5 holds true. Now I have to prove that 6 implies 7, where 7 is a statement which says that given any smooth curve gamma, every orthonormal basis at a point O gamma can be extended to a parallel orthonormal frame along gamma. So how to prove this implication? Suppose that gamma is defined on I, and suppose that B1, B2, Bn, this is the orthonormal basis of this tangent space. The idea is to extend Bi by considering the parallel transport this way we get Ei. This is a parallel vector field of gamma, which is a parallel transport of Bi, and the fact that 6 holds true, that is the parallel transport is an isometry, implies that bi bj, this is equal to, which is equal to ei t0 ej t0, will be equal to ei t ej t. And this formula says that ei t is the orthonormal basis for t gamma t m. That is, we have an orthonormal frame which is parallel. Okay. Now it remains to prove that 7 implies 4. Let's recall what is statement number 4. The statement number 4 is this one: if VW are parallel, along gamma, then derivative of VW, this is equal to dt v dtw. So if 7 holds true, then we can suppose that E1, E2, En is a parallel orthonormal frame along gamma. Then if V and W are vector fields along gamma, I can use this frame to write down a formula for V and W. So precisely I have V equal VI EI and W equal WJ EJ. Since EI are parallel, I have that dtv is just v dot I EI and dtw is w dot j EJ. So this implies that, in other terms, there is no derivative of EI and EJ. It is equal to 0. So this means that excuse me, I made a typo here. I'm so sorry. So this means that if I replace these two formulas into the right hand side of this other formula, I get Gij B dot Iwj plus Gij Viw dot j, where Gij is exactly Ei Uj. But this formula here is also the derivative with respect to t of this inner product here. How you can prove it? You just replace V equal to VI and W equal to Wj into this formula and you differentiate. So this is at the same time ddt of this inner product, but also star and this is the end of the proof of the proposition. Now I want to present an important corollary. One, the length of a smooth curve, the length of the velocity vector of a smooth curve gamma is constant if and only if dt gamma prime t is orthogonal to gamma prime t for all t in I, where I is the interval of definition of gamma, and 2 if gamma is a geodesic then the length of the velocity vector of gamma is constant. How to prove one? Simple. You use this formula ddt of Vw equal dtVw plus V dtW with V equal W equal gamma prime. If you make this choice, this is ddt of this square, and this is 2 times dt gamma prime, and the statement is immediate. If you want to prove 2, you use the fact that if gamma is geodesic, by definition dt gamma prime is 0, and using the same formula you have that gamma prime t has a length which is a constant. Uh, now I want to give you one non-trivial example of connection which is compatible with the metric. That is the proposition I proved a few minutes ago holds true for this connection. And this example is given by the tangential connection on an embedded Riemannian submanifold this is always compatible with the induced Riemannian metric. Please note that you must have an embedded Riemannian submanifold of Rn. This is a proposition that I don't prove. I leave the details to you. Because I would like to talk about another class of connections known as symmetric connections. And let's start our discussion giving again a look at the Euclidean metric, more precisely the Euclidean connection. I want to recall the formula. Nabla bar of y along x, this is xy1 ddx1 plus xyn ddxn. It is possible to prove that the Lie bracket of two vector fields is equal to xyi ddxi minus yxi ddxi. And now observing this formula, you may guess that this is true. For reasons that it will be clear later, we would like to work with connections for which an identity like this is true. So we give the following definition. A connection nabla on Tm where M is a smooth manifold is symmetric if this is true. For any x, y in Q of M. In some textbooks, you find that this definition is formulated in terms of a tensor. Known as torsion tensor, defined this way, tau of xy and you have that a connection is said to be symmetric if this tensor here identically vanishes. A non-trivial example of a symmetric connection is given by the tangential connection on an embedded Riemannian submanifold of Rn. So this connection here not only is compatible with the metric, but it is also symmetric. Why we look at metrics which are compatible, we look at connections which are compatible with the metric and which are symmetric. The answer to this question is provided by the fundamental theorem of Riemannian geometry. which essentially says that these two conditions here on a tangent bundle are enough to identify a unique connection. So let Mg be a Riemannian manifold with or without boundary. Then there exists a unique connection nabla on Tm that is compatible with G and is symmetric. Nabla is called Levi-Civita connection. Or Riemannian connection. So in Riemannian geometry, when we consider Riemannian manifold, we always work with a Levi-Civita connection. Proof. First we prove uniqueness. And second, we prove existence. Okay, let's start from A. So suppose that the connection gamma exists, then if I have three vector fields, then I can compute this. But also this. And also this. In each of these identities, you can replace the second summand in the right hand side. For example, by a sum of two terms using the symmetry. For example, let's look at this term here. this term can be rewritten as y inner product of y with nabla xz plus inner product of y with this early bracket. And you can do the same with this term and this term. Then if you consider this expression, that is, we adapt the first two equations and we subtract the third one, you get 2 times nabla xy comma z plus three terms involving the inner product of Lie brackets. This expression, this identity can be solved with for this term, and we get 1/2 times x y z plus y zx minus z xy minus y Lie bracket of x and z is not finished minus z Lie bracket yx plus x Lie bracket of z and y. So what we did is the following. Now we have a formula for the covariant derivative of y along x. Why? Because if you have the inner product of nabla xy with the elements of a basis of the tangent space, then you know nabla xy. Now suppose that nabla 1, nabla 2 are two connections which are compatible with G and symmetric. We want to prove that they they coincide. If nabla 1 and nabla 2 satisfies these two conditions, then you can write this formula for nabla 1 and nabla 2. And now we observe that the right hand side of this formula does not depend on the connection. So we have nabla 1xy inner product z equal to nabla x2 yz. So this is possible only if nabla x1 y is equal to nabla 2 yx, and this says that nabla 1 is equal to nabla 2. So this is the proof of the uniqueness. Now we prove that we have the existence. In order to prove the existence, we essentially use this formula for defining a connection. Actually, we will write down a version of this formula which holds true in local coordinates. So suppose that u x1, x2, xn is a smooth local chart. Then I can compute this using this formula. It is possible to prove that this is just 1/2 di of dj dl plus dj dl di minus dl di dj. This formula is true because it's immediate to see that Lie brackets of the delta I, delta j, this is always 0 for any I and j. Now we use the fact that gij is this, and we have also this one. If we replace these two identities in this identity, we get gamma ij m gml equal 1/2 di gjl plus delta j gil minus dl gij. how to get gamma ijk from this? Simple. This is the matrix representing the metric J in local coordinates. If we want to get gamma ijn, we have to multiply both sides by the matrix, which is the inverse of this one. Now we know that Gij inverse is GLM. Oh, let's use same index in here. So gamma ijk will be 1/2 GKL di GJL plus DJ GIL minus DL GIJ. So this formula defines a connection on a chart and it's not a problem when we have the overlap of two charts, because we already proved the uniqueness part of the theorem. So when two charts overlap, we have two different formulas for the connection, but they must agree. If gamma I jk is equal to gamma j ik, thing which is evident from this formula, if you consider a permutation of I and j, I mean you reverse the order, you will get the same value. Then the connection is symmetric. Why? This is true because if you take this formula here and you write this formula for x equal delta I, y equal delta j, you will get a formula where you have gamma ijk minus gamma jik followed by other factors. So this tensor here vanishes if these are equal, gamma ijk equal to gamma jik, which proves this implication. So we proved that a connection for which this is true is symmetric. It remains to prove that nabla is compatible with G. In order to prove this, we will use one of the statements of the proposition use statement 3 of the characterizations of metric connections proposition. That is gamma k I L GLJ plus gamma kjl is ek gij where we consider the special case EI equal delta I. So this becomes delta K Gij. Now, how to prove this formula? Simple. You use also the formula for gamma KIL GLJ and for gamma, sorry, I made a typo. Today is the typo day. I forgot something here. And for KJLGIL. So I was saying I use the formula for gamma IJM GML equal to something, and from this formula I get that this is 1/2 delta K Gij plus delta I GKJ the delta J GKI, and this one is 1/2 delta K GJI plus delta J GKI minus delta I GKN. If you add up, you will get that the left hand side, which is this, will be exactly equal to this. So I want to make a remark about the terminology. The connection coefficients gamma IJL of the Levi-Civita connection are called Christoffel symbols of G. I want to present the consequences of the theorem. Essentially, as a byproduct of the proof, we have that we got formulas for the Levi-Civita connection The first one is this one. One half and so on, and this one is expressed in terms of vector fields, and this one is not so easy to use because it's very long. It is known as Koszul formula. The second one is in terms of local coordinates. And is given by this formula here. Maybe it's a good idea to recall why this formula defines a connection, because this is gamma ij k delta k. So if you know gamma ij k, you know how to differentiate delta j along delta I, and you can differentiate any vector field y along the generic vector field x, replacing these expressions and writing this one in terms of gamma ijk. We have seen that you can write this one in terms of gamma ijk. It's not finished yet because we have two more formulas. So let E1, E2, En be a smooth local frame on a U open subset of M, and let Cijk be the n-cube functions defined by this identity Then there is a complicated formula for gamma ijk involving Cijk. So I have gamma ijk equal 1/2 GKL GJL sorry, GIL minus ELGIJ plus minus GJM CILM minus GLM CJIM plus GIM CLJM. Let me check if I copied correctly. Yes, I think it is correct, and so this is the formula for the Christoffel symbols in a local frame. And the last one is a special case of this one. Precisely, we consider a smooth local orthonormal case, frame. Note that before we did not impose the frame to be orthonormal. Then gamma ijk, this is 1/2 Cijk minus Cikj minus Cjki. Let's see very briefly how to prove this formula and this one. This one follows from this. If you use the hypothesis that the frame is orthonormal, then all these terms are equal to 0 or 1, and you have to use the fact that Cijk is minus Cjik. Instead, for proving this, use 1, that is nabla x, y, z, excuse me, another typo, equal 1/2 x, y, z plus y, zx, and so on. This is the formula given at the point number 1 with x equal ei, y equal ej, z equal el. And use the fact that gamma ij q times gql, this is nabla ei ej comma el. And then once you will have written down the formula for the right hand side, you can get gamma ijk multiplying by the inverse of this matrix here. And it is done. I think we can stop here for today.